Welcome to This Explainer. Today, we're putting on our code detective hats and diving straight into Lecture 12 by Skip Uni. We're going to get totally hands-on with a fundamental concept in C++ programming, the actual practical behavior of local and global variables. If you've ever felt a bit intimidated by coding or, stared at your screen wondering why your program is spitting out complete nonsense, you are in the perfect place. We are going to break this mystery down step by step. Okay. Let's dive right into this, because honestly, this is where so many really frustrating logic bugs are born. Imagine you've created a storage box in your program, a variable, but you completely forget to actually put anything inside it. What happens? Does the compiler throw an error? Does the whole program just crash? Well, instead of just talking about the theory, we're going to look at a live code crime scene of unassigned variables and see exactly how the compiler reacts. Section 1. The garbage value mystery. So let's treat our IDE like a laboratory right now. We've declared two integer variables just to perfectly isolate how different types behave when they're left to their own devices. First step, we've got a global variable, int x, which is declared entirely outside of our main function. And then we have a local variable, int y, declared safely inside the bounds of that main function block. Now, the absolute critical piece of evidence here, both of them are left totally blank. We declared them, meaning we asked the computer to reserve a spot in memory for them, but we haven't actually assigned a single value to either one. We run the program, execute a simple print command, and boom. The contrast in our terminal output is actually pretty shocking. Our global variable x prints out this nice, neat, totally predictable 0. But our local variable y? It prints out 421, and sometimes you'll even see a bunch of other completely random numbers trailing right after it. It's just absolute chaos. So why exactly did the compiler treat these two empty boxes so differently? Well, this brings us to the formal definition. The garbage value. This practically proves a massive, absolutely crucial rule in C++. If you don't assign a value to a global variable, the compiler actually has a built-in safety net. It automatically defaults that global variable to 0. But local variables? Yeah, they have no safety net whatsoever. If you leave a local unassigned, it just grabs whatever random leftover memory junk happens to be sitting in that specific memory block at the time. It could be 421, it could be 1,000,000, it could be a negative number. That is a garbage value. And if you accidentally use it in a mathematical calculation later on, it will literally ruin your program's logic. Section 2. Assigning values correctly. Knowing the danger of those garbage values, we absolutely have to shift our focus to the solution. And it comes down to 3 simple, non-negotiable steps. Step 1, you declare the variable, claiming your space in memory. Step 2, you initialize it. You immediately assign a value to it, especially if it's a local variable. You just never want to leave a local variable hanging. And step 3, you execute safely, knowing exactly what data your program is manipulating. As a programmer, you have to get into the strict habit of always initializing your locals to keep your software predictable. So let's take our own advice and go back to the code. We assign the value 20 to our global variable x, and we initialize our local variable y with the value 10. We save, we hit run again, and perfect. The program successfully prints exactly what we expect, a 20 and a 10. Order is totally restored to our code. But hey, our investigation is not over just yet. We solved the garbage value mystery, sure, but what happens when variables start fighting over the exact same identity? Section 3. Name clashes and precedents. We are setting up the ultimate showdown in our code. We've gone right into the local block and changed the name of our variable from y to x. This creates a direct head-to-head conflict. We now have a global x sitting outside main holding the value of 20, and a local x inside main holding the value of 10. If we write a command that simply says print x, which one is the compiler going to choose? Seriously, take a second and try to predict what you think is going to happen here. This setup brilliantly illustrates the structure of our clash. We have 2 identical variable names occupying 2 completely different scopes. Think of the global scope kind of like a national television broadcast. It covers everything, the whole country knows about it. The local scope, on the other hand, is strictly like a local neighborhood radio station. It only broadcasts inside its specific little block. When you are standing inside that specific neighborhood, inside that local block, whose voice do you think is going to be louder? The answer is 10. When we execute that print command from inside the main function, the compiler prints 10. It completely ignores the global x holding the 20 and chooses the local variable's value instead. The local radio station completely drowned out the national broadcast. So, the absolutely crucial point to take away is this. Local variables always take precedence in their specific block. When a naming conflict occurs, the compiler will always give priority to the most local, most immediate variable it can find within those curly braces. It basically assumes that if you're asking for X from inside the local neighborhood, you mean the local X, not the global one. Section 4. Key Programming Takeaways. All right, we've run the experiments, we've solved the mysteries. Here is your ultimate cheat sheet to remember. First, unassigned globals default to 0. It's a great safety feature, but definitely don't abuse it. Second, unassigned locals get garbage values. These are random memory leftovers that will absolutely crash your math logic, for sure. Third, because of those garbage values, you must always initialize your local variables the exact moment you declare them. And finally, if a name clash ever occurs, the local scope wins out over the global scope. Mastering these foundational rules is just so essential for writing robust, bug-free C++ code. But I want to leave you with one final, kind of provocative thought here. We just proved that local variables always win in a name clash. But what if you really desperately needed to access that global X of 20 from inside that local block? Is the global variable just lost to us forever in that scenario? Or is there maybe a secret C++ technique, perhaps a specific symbol or operator, that can actually force the compiler to look past the local neighborhood and fetch the global value? Well, I'm going to let you ponder that scope resolution mystery for our next session. Until then, keep experimenting with your code, keep those variables initialized, and I'll catch you in the next explainer.